Hello, good morning, SARS. Good morning, Mars. Thank you for subscribing to this training. Now, in this video, I'll attempt to show you how you can run your regression analysis. Now, I did share a document with us carrying just a brief of what regression analysis is all about. Now, in the document, uh, I tried to define what regression analysis is, and we say regression analysis is a statistical method which you use to estimate the relationship between a dependent variable and one or more independent variables. And regression analysis is more like it's a cause and effect analysis, and analysis you do to see how, let's say, factors that affect your production. You want to see how uh, the various subsector in the economy affect the GDP. Now, of course, if you're doing that, which is a time series analysis, it has another protocol, although it makes use of regression analysis. It's a regression analysis and makes use of OLS estimation technique. Now, you also want to look at factors that affect loan repayment for the bank, for those guys in the banking sector. You want to look at factors that affect plant yield. You want to look at factors that affect behavior. So when you do all this kind of analysis, a cause and effect analysis is basically called a regression analysis. And regression analysis can be subdivided into simple regression, multiple, or non-linear regression. Now, based on the estimation technique, we can classify regression analysis into ordinary least square estimation technique and maximum likelihood estimation technique. Now, this has to do with econometry, so you might not need to disturb yourself as such with this, but you just have to know that based on the objective you have for your that you want to achieve, the aim of the carrying out the analysis, you have to know which of the technique you are working with, because each technique has some models under it. Now, the functional form under OLS, which is ordinary least square regression analysis or estimation technique. We have the linear functional form, we have the Cope-Douglas, or as some we call double log functional form, which others are semi-log. Semi-log can be subdivided into log linear or linear log. There's the transcendental and others that make use of OLS. Of course, Tobit model make use of OLS as well. While we have the maximum likelihood estimation technique, which I just classify it for the purpose of this training into binary models and others. In binary models, we have the logit models, we have the probit model, we have ordered probit, we have ordered logit, we have multinomial logit, we have multinomial probit. The order regression, the switching regressions, and of course, others here we still have a propensity score matching, which makes use of maximum likelihood estimation technique. It basically makes use of probit and a combination of matching technique and the switching regressions. So it's the list is enormous. It's a nested regression. So it depends on what you want to achieve. That's where you decide which of these techniques to use. We have generalized least square, other techniques to use, the percentage least square, total least square. These are all econometrics. But for this basic, the purpose of this class, we are just going to we'll just focus on the linear model and touch a little on Cope-Douglas model, which is the basics that almost everybody use. Now, from my screen, this is the general regression model. So whatever the model you decide to use, this is the way you represent it generally in implicit form. The y there represent the dependent variable. This is your constant or intercept. This is the slope or the coefficient. Then the x here is the independent variables, while of course the error time. We see most times that there's always an error which will be left behind because the regression model is not perfect. The independent variable will not completely explain the variation in the dependent variable, so there will be error which will definitely be due, as we assume, to variables that are not captured in the model. And going forward, like every other analysis, regression analysis has its assumptions. So you can read the assumptions. Now, while all other assumptions may hold for a time series analysis, for a cross-sectional analysis or a cross-sectional data, time series data as it were, and a cross-sectional data, we focus more on heteroscedasticity. Now, and also we look at the normality. Now you can do, this is a pre-test before the analysis. In the process of cleaning your data, you want to use Shapiro-Wilk test to test if your dependent variable is normally distributed. Another pre-test you do before carrying out the analysis to look out for outliers. If the outliers, you can identify outliers and treat it properly. Like I discussed initially, this has to be stated in your protocol, your sampling protocol, how you're going to deal with outliers. Will you winorize it? How you intend to deal with it? So after running out the Shapiro-Wilk test, which should not be significant, then you decide on how you treat that variable in question or that respondent. Now, the heteroscedasticity assumption, it's not supposed to be significant as well. This is a post-estimation analysis. This is a pre-estimation analysis. The normality is a pre-estimation. But others hold strongly for time series analysis, the time series data. The other forms of data, a point in time, like you call the cross-sectional data or experimental data, the ones you get in the field almost immediately. Time series analysis, data you collected over a period of time, and there are also panel data as well. Okay, now this is an explicit presentation of a regression model. So this is a linear form, and this is a Cobb-Douglas form. And the linear form is not having the natural log attached to it, while the Cobb-Douglas is having the natural log. Now, from experience, the Cobb-Douglas regression analysis will give you a better result, to give you a better coefficient. And also, why you always prefer a Cobb-Douglas is because the model is twice differentiable, but this is not twice differentiable, of course. So it's always advised you go for the Cobb-Douglas regression analysis. Now, from the explicit model I presented here, I'm saying Y is output. So let's say I'm calling it quantity harvested. This can be loan disbursed. This can be GDP. This can be crop yield. This can be crop height. This can be soil moisture. Whatever it is, which is dependent variable. Why the X now can be for here now. These are the input variables that would affect the output. Now, another thing I want to quickly point out is when you carry out a regression analysis, make sure that your model follows the theory. I see people run regression analysis and you're trying to look at the factors that affect the yield of crop, for instance. And in the factors, instead of you to mention the core things that from theory will affect the yield of crop vis-a-vis the soil, the kind of soil, probably with the fertilizer you use, maybe the humidity, relative humidity, rainfall, the thing from theory, the variables from theory that will actually affect crop yield. I see people deviating and they go ahead and start putting variables such as the sex of the farm, socioeconomic variables of the farmers, which should actually, even if you're going to add it to your regression, it should come in as control variables. Now, control variables are variables you put after you've keyed in the main input, the main variables that affect the analysis. You put them at the tail end. So for instance, if I want to put control variable here now, I can put X6. I can now put education. X7, I can now put maybe marital status. So you put those kind of variables to reduce the coefficient. Probably your coefficient is coming out, the figures are high. You just put it to reduce the coefficient. And another thing I also want to address quickly with this video is the variables age, education, and farm experience should not be in one regression analysis because they co-move. And when you put them together, you can't avoid the problem of multicollinearity. They co-move because as the age increases, there's every tendency that the person's education is going high, and there's every tendency that the experience is going high. So it co-move. So we always advise that when you want to do analysis, you pick experience because we say experience is the best teacher. So in the place of age and education, you put experience and drop the other variables because we know they co-move. Now, going forward, this is a sample of the output from SPSS. Now, to quickly carry out this analysis, let me just show you that you launch your SPSS. So mine is launched. So the next thing you do is to come and open your data set. So I come to File. So I click on File. I click on Open. I want to open Data. So I click on Data. Now you locate your data. Mine is on the desktop. If yours is not on desktop, you just look for the directory where it is. So mine is on all the folder. So mine is on the desktop. So I come. This is the data I want to use. Production data. So if you look from my screen now, you discover that what SPSS is giving me, it's data that are saved in SPSS format. If yours is not saved in SPSS format and probably is in Excel spreadsheet, all you need to do is come here. You click on this file type and click on Excel. So it will produce, you see it has automatically produced data that are in Excel spreadsheets. So let me quickly go back here. I want the data in SPSS format. I want my data set in SPSS format. So I want to open production data. I highlight, then I click on open. You can double click. So this is my data set. So like I said, you can check for outliers using a scatter plot. You can test for normality using Shapiro-Wilk test. I will attempt to do another video that I will share later on for you to learn how to do Shapiro-Wilk test. Now, the analysis for Shapiro-Wilk test is not supposed to be significant when you test it, depending on the null hypothesis you might have stated. But I think the null hypothesis from the null hypothesis is not supposed to be significant. Now let's go to the regression proper. Now I will run a linear regression analysis. So first thing, like I said initially, you want to just look at the nature of your data. So I run a descriptive statistics. So I come to analyze, I go to descriptive. I just want to see how the variables are distributed. So you can highlight the one and just click the arrow key. But to save you time, just highlight one, hold down your left cursor. No, sorry, hold down the shift key and highlight the rest. The shift key and highlight the rest just by clicking on it. Then you move it at once. So I just want to see if there are missing variables. So I uncheck the mean, uncheck this. I just want to see the summary or the sum. So I can click on continue. Okay. So from here I can see now that there's no missing variable. I have 292 across board. So there's no missing variable. So I'm set. I can go and do my regression analysis. I come back to analyze. I come to regression. I go to linear. I click on linear. So my dependent variable here is output. So I click on output, which is the dependent variable. Now, my independent variables, I pick the rest. So I hold the shift key, take it down. If you observe, this my data look more like a profit function or a cost function. Better still, that's the best word. You discover all my units are all in cost naira. So it's also good you have to state your unit of measurement. If you are using height, if you are using width, you state your unit. All right, so I bring it down here, all here. So the next thing I want to do is I want to check for the I want to see the Durbin-Waxton statistics. You don't need to really disturb yourself about this, but this is one of the tests you want to check for one of the assumptions. You just want to check for this and see the assumption, but not for a cross-sectional data. You don't want to disturb yourself about it, but of course, let's just speak it. The figure is supposed to be within the range of minus plus 2.00. 2.00, it should be minus plus 2 better still, let it be within the range of 1.98 to 2.02. That is the range you're expecting for the results to be okay. So you click on continue, and that's all. I think you don't need any other thing. You just come and click OK. So from this analysis now, this is the regression output. So this is my R square. This is my Durbin-Waxton statistics. So because it's a cross-sectional data, you don't really disturb yourself about it. But if based on your assumptions or the protocol you stated, this is expected to be okay, then you might need to work on your data or probably clean it properly to make sure you scale this up. But usually I would say don't disturb yourself about this. Now, this is important. This is key. It has to be more than 50%. Depending also on if you want to look at the strength of the relationship, this has to be more than 50%. It's advisable is more than 50%. And then this is the R square. Then the F statistics has to be more than 3.5. So it's above 3.5 and is significant. Now this is the coefficient results. The result from the coefficient based on so this is x1, x2 that is stated in the model down to x maybe 6 or what I have here. So I want you to watch this video. I will share the data set and I want you to have results. Then during the class in the training session, or ask questions and we'll try to interpret the results. A brief interpretation will be this shows the extent of variation. The R square shows the extent of variation in the independent variables. Now the F statistics shows if all the independent variables could move, are they significant in affecting or influencing the dependent variable, which is true because it's significant. Then the variables here show the individual contribution of each of the independent variable to the possible change in the dependent variable. So we see here that seed cost is significant, cost, land preparation cost is significant, planting cost is significant. I think that's the three variables that are significant. Then this is the residual statistics. Alright, thank you very much for watching this video. We'll see you in the class. Thank you.